All right, but before we do that, let's do a little warm up. Okay, it's our composition using multiple things. We've got an inverse in there. There's lots of different things going on there. So just kind of a review. All right, so they tell me h of x is defined by the table, f of x is defined by the graph, and if you look really closely, they tell me that g of x is right here. This is this expression. G of x equals the square root of 14x minus 3. Okay, so they hit it there for me. The first thing they wanted us to find was h of f of 4. So if we're doing a composition, we're going to start on the inside to find f at 4. So I'm going to go over 4 on the graph. What's my y value? 3. So now I'm looking for h at 3. Well, that's going to come from the table. So I go to the table. When x is 3, what is y? 5, and that's my answer. Okay, so just working inside out. Likewise, when we do the next one, this time we're going to start with h. So h at 3 is going to come from my table. We already said that was 5. And so now to get my final answer, we're going to go to the graph. When f is 5, what is y? It is 4. Okay, so just reading our different representations. All right. The next one, we want f at 7. All right, f at 7 on the inside. So we're going to start there. F at 7. What's that y value? 2. And then to get my final answer, we're going to have to plug it into g. Well, g was where they gave me an algebraic expression. So we're going to plug that in. 14 times 2 minus 3. That'd be 26 minus 3. No, 28 minus 3. Square root of 25, which would be 5. Okay. All right, so here again, we look about an inverse for h, okay? Remember, when we're doing an inverse function, the x's and y's switch places. So for h inverse, x is the second column, y is the first column. And so if I want h inverse of -4, we're actually going to start in that left-hand column, all right? So when that value is 4, what is its corresponding y value? 2. Okay, it is 2. So you have to go backwards on that one. Okay, like we have switched the x's and the y's, right? And then on E, we've got g inverse of 9. Okay, so let's think about that for a second. G inverse of 9. So if I have x and g of x, then I would have x and g inverse of x. So let's just think about this for a second. If I want g inverse of 9, what was it, an x or a y value in the original equation? Okay, if I want g inverse of 9, so this is my inverse x value, what would that value have been in g, an x or a y? It'd be the y, because they switch, all right? So to find the value of that function, we're going to have to take my g function and set it equal to 9. What was that original x value? We don't have a function for g inverse, so we're going to solve it this way. Okay, using what we've got there. How would I undo that square root? I'd square everything. All right, so I'd get 81 equals 14x minus 3. Then what? Add 3, so I'd get 84 equals 14x. And to get my final x value, we would divide by 14. And so x is 6, and that's what I was looking for. All right, that was probably the toughest one on the paper. All right, just because of how it was represented. Right. Last one says a challenge, but it's really not that hard. When we do multiple compositions, where do we still start? In the inside, okay? So we're going to start with h at 2, which means I'm going to have g and an f and a new value in there. What is the h value at 2, original function? It's 4, okay? So then we're going to find f at 4. That's going to come from my table. So when I do that, f at 4 is 3. And then to finish it up, we're going to do g at 3. So we're going to plug 3 into the g function. So square root of 14 times 3 minus 3. Let's see. 42 minus 3 is 39. And we're done. Okay. Questions about any of those? That's a good review of all that inverse stuff and composition stuff that we did on Friday. More than likely that would be on a non-calculator section, so that the square root would be fine. And I don't want to say this yet, but I don't think we have to simplify radicals. I'll go back in and look at my notes just to be sure. I know in calculus we don't, but things are a little bit different with the AP exam for pre-cal. Okay. All right, rock and roll. But let's look at what we're going to talk about today. Okay, we're going to dig more deeply into logarithmic functions. And we're going to build everything off of fact that we know that they are exponentials and logarithmic functions are inverses. Okay, so our learning targets today are to construct representations of the inverse of an exponential function with an initial value of 1, identify key characteristics of log functions, and then rewrite logarithmic expressions in equivalent forms. If you remember, the last time we did 3 lessons, it was all for exponential functions, the exact same things. Okay, so we're just going to repeat that today for logarithmic functions, really the only difference. Okay, key question number 1, what is the relationship between an exponential and a logarithmic function? Not opposites. Opposite implies a change in a sign. They're an inverse. Okay, they are inverses of each other. So we want to be sure we're using the right notation there. Okay. You knew what you're talking about. We just need to use a different word. Okay? They are inverses of each other. All right? Super important. They will undo each other. Okay? Let's look at a tabular representation of an exponential function and a logarithmic function. Okay? When we look at the exponential functions, if we're thinking about the inputs and the outputs, okay, what do you notice happening with all the x values? Yeah, they're increasing by 2. They're equally spaced. So in an exponential function, our inputs are equally spaced. Okay. And then what about our outputs? How are we getting those y values? We're multiplying by 2. So we say the outputs are multiplicative. All right, meaning we're just multiplying by something. That's a good word, though. That's an SAT word. All right. They are multiplicative. Right. Well, if exponential functions and logarithmic functions are inverses of each other, what's going to happen to their inputs and outputs? They're going to switch. Okay, they're going to switch. And so if I'm trying to identify a logarithmic function, we're going to switch it and say, well, their inputs are going to be multiplicative. And their outputs are equally spaced. Okay, and that's how we can tell the difference between a logarithmic and an exponential table. All right, exponential functions, we're going to add for the inputs, multiply for the outputs, or add for x, multiply for y. For logarithmics, we're going to multiply for x, add for y. So it just switches, okay? That inverse concept, they switch, right? So let's take a look at a few tables and see if we can figure out, okay, are they exponential, are they logarithmic, are they neither of those things, okay? So let's flip that over and let's take a look. Okay. Take a second look at those tables. See what you think. All right, let's see what we think. On that first one, what do you think? Exponential, logarithmic, or neither? It is definitely exponential. Okay. If we look, the x's are going up by 1. The y's are being multiplied by 1/2 or divided by 2. Okay. All right, what about B? Logarithmic. Okay. If we look at the x's, we are multiplying by 3. The y's, we are adding 10. All right. What about C? It's neither one, right? So it looks like on the first, on x's, we're multiplying by 10. And on y's, we're multiplying by 2. That's neither one of our characteristics, okay? So it's neither. And then what about the last one? It's logarithmic, okay? If we look, we're multiplying by 2. And what are we doing over here? Subtracting 3 each time, okay? So that's the difference in those two tables. Questions about that? Identifying logarithmic versus exponential functions. Okay? All right, cool. Let's look at the next one. All right. One of the things that we said about inverse functions is that their compositions equal x. Okay? And not only do we have to do one, we have to do both. And so let's kind of walk through those and see if we can prove that to be true. 3 to the x and log base 3 to the x. Okay, so my f function is 3 to the x, my g function log base 3. We're trying to prove that they are indeed inverses. So when I look at this one, I want f of g of x, which means everywhere that I have an x in f, I'm going to plug in that log base 3 of x. Okay. Well, we know exponential and logarithmic functions undo each other. So if I have a log and an exponent, what's going to happen? What do inverses do? They cancel each other out. They undo each other. So all that mess goes away, and what's left? Plain old x, okay? Plain old x is what's left. Okay. Let's go the opposite direction. All right, we want g of f of x. So my f function was 3 to the x. So everywhere in my g function that I have an x, I'm going to put that expression 3 to the x. So I have log base 3 of 3 to the x. Okay, so I have a logarithm that has an exponential inside of it. What are they going to do to each other? Cancel out. And all I'm left with is that x. Okay, so that composition still holds true, all right, for inverses. All right, let's look at number 3. This one's, again, is graphing, okay? It tells me that they graphed k of x for me, which is 2 to the x. And they want me to sketch a picture of the inverse log base 2 of x, okay? Now, for me, one of the easiest ways to do that is to think table of ordered pairs, all right? So if I look at the function that's graphed there, let's just pick a few points that we can see well. I can see 0, 1, and I can see 1, 2, and I can see 2, 4 pretty decent, okay? So that is my k function right there. Right? If I want ordered pairs for k inverse, what's the only thing I have to do? Change the x's. Yeah, switch the x's and y's. So I have 1, 0, 2, 1, and 4, 2, and that's what we're going to graph. 1, 0, 2, 1, and 4, 2. Okay? Now, looking at that exponential function, it has a horizontal asymptote. If everything switches, what kind of asymptote are we going to have on our logarithmic function? Vertical. Okay, this is the line y, bless you, this is the line y equals x. Remember, they are reflections over the line y equals x. That's why we can switch x and y. So there's my picture. All right, and then the last one, kind of talking about the whole properties of inverses and how all that works. This is an interesting question. Notice again, it comes up and it's asking me for an average rate of change. Guys, that's going to be something we see from now until the end of the course, all right? For every type of function we encounter, they're going to ask us to address an average rate of change, okay? Now, let's take a look at what we have. It tells me that the exponential function h of x contains the points 2, 3, and 6, 27. Okay, so that's my exponential function. Then it says, find the rate of change of y equals log base a of x. One of the things we have to recognize is what's true about h and that new log function. What's their relationship? They're inverses, okay? And so if the original function has the points 2, 3, and 6, 27, what's my inverse function going to have? What are its points going to be? 3, 2, and 27, 6. Okay? So when we see that they've asked me to find the rate of change over the interval from 3 to 27, those are my x values for my inverse function. Okay? How do we find rate of change? Well, it is change in our y's over change in our x's. All right? This time we want to do it for our inverse function. So if we look up there at those points, what are the y values for my inverse function? 6 and 2. And what are the x values? 27 and 3. Okay, and then we just simplify. So it's going to give me 4 over 24, which would reduce to 1/6. Okay, so questions about that inverse relationship. It all hinges on switching x and y. Okay, that was learning target 1. Congratulations. Cha-ching. All right. I think it's funny when they do the Mario coin thing when y'all hit baskets at basketball game. The first time it happened, I'm like, because I'm old. Did y'all hear, what is that noise? Anyway. So then they had to fill me in because I'm slow, but it's all good. And I didn't play video games growing up. Like we had an Atari. So like my knowledge of video games is Pac-Man and Frogger. Okay, that's it. Okay. All right, so let's jump in here. Let's talk about key characteristics of logarithmic functions. All right, we know they are inverses from exponential. So I want to kind of draw on what we know about exponential functions, okay? Our general form is going to be this: y equals log base, rewind, a times log base b of x, okay? A times log base b of x. That's our general form, okay? Couple of rules. The base has to be greater than 0, all right? So we can't have a base of 0. My coefficient, can't equal 0, and my base can't equal 0, all right? And then the last thing, all right, x has to be greater than 0. All right, so there's just a lot of rules when it comes to logarithms. Okay, so the number in front can't be 0 because then I wouldn't have a function. The base can't be 0 because then again, I wouldn't have a base for my exponential function. All right, and the number inside, the value inside of the logarithm has to be greater than 0. That's really important. Okay, that being said, let's talk about domain and range. Right? When we think about an exponential function, right, so it just grows forever or it decays forever, what was its domain for an exponential? Negative infinity to positive infinity. So what's that going to match in my logarithmic function? The range. All right, so negative infinity to positive infinity. Okay? So again, I'm pulling that as the opposite from my exponential function. So like if this is an exponential function, all right, so this is my exponential, and I'm trying to switch everything, okay? Now, thinking about the exponential, what would my range be on that? 0 to infinity. Well, that's going to match the domain of my logarithmic function. So my domain is going to be 0 to infinity, okay? Now, another way that I like to write that is because we know that exponential functions have horizontal asymptotes. So logarithmic functions are going to have vertical asymptote. I say it's my vertical asymptote to infinity, okay? Because my asymptote is going to move. It's not going to always stay at 0. All right, so I drew 2 pictures here. Well, I didn't do it, but somebody did, of 2 different logarithmic functions, which ways they can go, right? Or that we're going to consider. When a is positive and my base is positive or is greater than 1, it's going to be an increasing function from left to right, okay? When a is less than 1, in other words, when I have a negative in front and my base is still greater than 1, we're going to have a decreasing function. Now, just like exponential functions, logarithmic functions always increase or decrease. Okay? They never switch. So there are no relative extrema. Okay? So they either always increase or they always decrease. So there's no relative extrema. And then the nice thing also is that applies to concavity, just like it did with our exponential. They're either always concave up or always concave down. So no points of inflection. Now, in behavior, okay, little different from what we would do with an exponential function. I want you just to kind of look at the 2 graphs that we have up there, okay? On both of those, as x approaches positive infinity, what's the graph doing? One of 2 things. Yeah, it's approaching positive or negative infinity, okay? But on the left side, what do we always approach to start? Yeah, we don't approach negative. The values approach negative or positive infinity, but what does the x value get close to?
0.
Yeah, 0 or the asymptote, okay? So the thing to remember about your in behavior, it's no big deal if we're going, all right, the limit as x approaches positive infinity. We're going to definitely do that one. It'll always be positive or negative infinity, okay? So that will always be true. I guess I should put f of x in there, okay? But the left in behavior, okay, will always approach the asymptote from the right, okay? We never go from the left of the asymptote because logarithms aren't defined over there, okay? We'll always approach the vertical asymptote from the right. Okay, so let me show you what that looks like. That limit, okay, and I'm going to say vertical asymptote with a plus, okay? We're going to always come in from the right of f of x will be plus or minus infinity, okay? So this will always be your left hand statement. The other one will always be your right statement. Okay. So a little different right there from what we've done in the past. So let's take some pictures and let's see if we can do the in behavior, okay? For most of us, that seems to be the tricky part for what we do with all of these when we get to those limit statements. Okay, remember, a limit's just telling me the behavior of the y values, all right? That's all it's doing. Any of y'all be 18 this summer? Be sure you register to vote. You'll be able to vote in November. That'll be exciting. Okay. crazy. Y'all are going to be 18, right? Anybody not 17 yet? Like you turned 17 like this spring. Okay. Anyway, it's still exciting. I don't remember much about 18 other than my mom got me a pair of earrings. No. What did she get me? I don't remember. Anyway, but I went and got my second holes done. If you knew my mother, that's a no-no. Just like when I put hot pink in my hair when I went to the beach when I was 40. She didn't like that either. But it's all good. It's okay. It's really not that big a deal. So, but to her it was. So when I got my tattoo, she really lost her mind. I was 48. Anyway, okay. No, I was 49. All right. But Rebecca broke the ice for us. She came home last Christmas and got a big one on her back. And so then the rest of us were like, hit me up. She took all the stress from my mom, so it's all good. All right, so let's take a look at these. All right, we want to write limit statements for the end behavior of these following functions. We got to think about it. The first one gives me a picture, okay? And to help us notice, it says for the left as x approaches 0. Why did it choose 0? That's my vertical asymptote. Okay, it shows 0 because that's my vertical asymptote. What are the y values doing as I get close to that asymptote? Where are they going? They're going down, so they're going to negative infinity. Okay, on the right side, it's always the limit as x approaches positive infinity. Okay, and so as I go to the right, which way are my y values going, up or down? They're going up. So positive infinity. Okay, see if you can do the next one. All right, on that left-hand side, we want to approach the asymptote. What's the asymptote? 0, okay? So we're going to take the limit as x approaches 0 from the right. And which way are our y values going? Up, so positive infinity. And then we're going to take the limit as x approaches infinity. So as we go out to the right, what are our y values doing? They're going down for real. All right, so now let's look at the last one, okay? They didn't give me a picture, all right? But I've got 2 times log base 3 of x. So this is where we got to kind of think about which one of these pictures is this going to be, okay? I have a positive number in the front and 3 there is greater than 1. This is where those pictures right there in the middle of that chart. All right, so which one's it going to be? The first one or the second one? Are we going to be an increasing function or a decreasing function? We're going to be an increasing function. So because we're going to be an increasing function, it's going to look something like this. How do I know that the asymptote stayed in the exact same place? It's a good question. Can't assume. You know what that does? Makes up out of you and me. All right, so we don't want to assume. All right.
Because when you plug in 0.
All right, so here's the deal. Did I move this logarithm anywhere left or right that would move my asymptote? No, there's no translation to it. So that's why we know that the asymptote stays at 0. We didn't move it, okay? We're going to do one in a second where we do, all right? So that being the case, it's going to look just like the one at the first one. So the limit as x approaches 0 from the right, oh, that's g of x, not f, sorry. It's going to equal negative infinity, and the limit as x approaches infinity of g of x is going to be positive infinity. Okay, so question about end behavior. All right, cool. Let's throw it all together. Okay. Let's throw it all together. Yep. This is what we're doing. We're not done with the second one yet. We're going to practice it, but we've covered it. I saw those. I saw that eye roll, Callie Beth.
But do you think that it is done down there on the floors? Because it doesn't.
Okay? I still love you.
It's just a natural.
I know. That's what Rebecca used to say. And then I would say the typical. So let's look at this first one. We want to graph log base 3 of x. Now, I don't know about you, but I struggle to graph logarithms because to plug in values for x like we would for like x squared, x to the third, is a little more difficult, okay? So here's my trick. I use what I know about inverses. The inverse would be 3 to the x, and so I get some ordered pairs, okay? I know 3 to the x, all right? So if I plug in 0, what's 3 to the 0? 1. And what's 3 to the first? And what's 3 squared? 9, okay? I know for my log function for f of x, it's the inverse of those ordered pairs. In other words, I just switch those points, okay? So 1, 0, 3, 1, 9, 2. Those are the values we're going to graph, okay? Did I translate that logarithm anywhere? No. Okay, there's no parentheses, there's no dilation in the front, there's nothing added or subtracted. Okay, I start with the base as a base as a base. Okay, so my exponential function is 3 to the x. I pick some x's, plug them in to get my y's. For my inverse, which is my log function, I just switch them. Okay, so now let's graph those points. 1, 0, 3, 1, and 9, 2. If you're doing the copied one, I'm sorry, the graphs didn't copy very well. Okay. Where's my asymptote going to be? At 0. Okay, so I'm going to mark it in so that when I do my curve, I don't get in the way of my asymptote. Okay, so use what you know about inverses. It will help you. All right, let's answer some questions. What's my domain? 0 to infinity. I can do that just looking at it. Okay. What's my range? Negative infinity, positive infinity. All right. Where's my x-intercept? 1, 0. And what's my asymptote? Not y. X, because it's vertical. Okay. Is this function increasing or decreasing? Is it concave up or concave down? Down. And then it's in behavior, we do the two limits. Limit as x approaches my asymptote, so 0 from the right of f of x. Where's it going? Yep. And then the limit as x approaches infinity. Where's it going? Positive infinity. Okay. So that's just a basic one. All right. Now let's make it spicy. All right. Let's make it spicy. The good news is we're going to still be able to do all the same things. Okay. First thing I notice when I look at this function, log base 4 of x plus 5 and then subtract 2, is it sitting somewhere? Oh, okay. Back up. Has it been moved around?
Yes.
Yes. Okay, let's say it that way. It has been translated. How do we know it's been translated?
Because
There's a bunch of extra crap up there. All right? There's something in parentheses. There's something at the end. Like we've moved this bad boy around. Okay? So the first thing I want to talk about is my translation. It looks like I would send it which way, left or right? Left 5 and down 2. So I'm going to do that first. Okay? I'm going to go left 5. So 1, 2, 3, 4, 5 and down 2. And I'm going to put a little X there. And I'm going to treat that like my 0, 0. Okay? I'm going to treat it like my origin. All right? For just a second because we know we've moved it. Well, now let's think basics. Okay? Let's think basics for log base 4. What would be the exponential function we might start with to get some ordered pairs? Yeah, 4 to the x. All right, 0, 1, 1, 4, 2, 16. Okay, well, those aren't the points I need. What do I need to do with them? Yeah, switch them. So 1, 0, 4, 1, 16, 2. So from that little x, those are the values we're going to graph. Okay? So let's do that. All right, from a little x, 1, 0, 4, 2, 4, up 1, and then 16. I think I got enough. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Close. Okay. So we take it up a little bit. Okay. Now, before I draw my curve, where's my asymptote going to fall? Is it at 0 now? In the middle? Yeah, I moved it, right? I pushed my origin back. I pushed it back to here. Okay? I pushed it back. And that's going to help me, right, to figure out all of my good stuff. How far did I push it back? 5. Okay? Came from right here. All right, I pushed it back 5. So my asymptote is going to be here at x equals -5. Okay? Pushed it backwards. It's that horizontal translation because we have a horizontal asymptote. Right? So my horizontal translation is my horizontal asymptote. Now let's answer everything else. What's my domain? -5 to infinity. What's my range? Yep, all real numbers. What's my x-intercept? It's actually 16. Okay, now let's say that we didn't know that. Okay, we didn't know that. One of the things we can do is to solve that equation. Well, that's our lesson for tomorrow. Okay, so we'll talk about that tomorrow. Okay, if you don't remember how to solve a logarithmic equation. We were able to do this one just by our points because of where it landed. All right, increasing or decreasing? Concave up, concave down. Down. And then we could do the in behavior. The left one's going to be the limit as x approaches what? -5 from the right. Good. Of f of x, we'll just call it f of x. And it would be a negative infinity. The right one is always as we approach infinity. Okay. Questions about those two? Okay. All the different characteristics of the graph, understanding where the asymptote comes from that vertical translation. Okay. When it's an exponential function, the horizontal asymptote comes from, nope, just kidding. It comes from where we move it up and down, right? Okay. Anybody need the AED? Yes, ma'am.
On the ones above here, it says that, on the chart, it says key characteristics, and it says that A cannot equal 0, and have an A value.
Yes, we would assume it's 1. Yes, good question. So there was no dilation in the front. Yes. Okay. All right, let's look at these two. I like these. So it tells me that we've got logarithmic functions here. All right. And it wants me to find these values in my table that are missing. So we've got to think a little bit about what log functions do. Okay. We know in log functions, the x's should be multiplicative. The y's should be additive. Like we add something to y, we multiply on x. Okay. So take a look and let's find our k. So here's what we're looking for. I'm looking for k right here. All right. If I look in this table, all right, I should be multiplying in my x's. So what would I do to go from 1 to 2? Okay, what would I do to go from 8 to 16? Okay, I think that's what we're going to do. All right, so then what would K be? 4. Good. See, that's not hard. Just understanding about the table. Ooh, now this one just looks a little different. Okay, it's got E's in there. All right, it's got E's. And we've got K again right here smack dab in the middle of the table. I'll be honest with you, when I first saw this problem, I was like, I don't know. I jumped away from the negative values, okay? Because we got to think exponential function, all right? I want to know, what am I multiplying e to the 7th by to get e to the 10th?
E to the third.
E to the 3rd. Okay, so let's see if that holds true. If I take e to the negative 2nd times e to the 3rd, do I get a plain old e? Indeed I do. Negative 2 plus 3 would be e to the 1st. And so to get the k that I'm looking for, oh, that was a Star Wars reference. Okay, so e to the 1st times e to the 3rd would give me k, and so what's k going to be? E to the 4th. Okay, so don't let crazy representations freak you out. You just got to think a little bit. Okay, just got to think a little bit. Question on those two. All right, learning target 2, check. Okay, learning target 3. Hopefully these look familiar to you. Properties of logarithms. Okay, properties of logarithms. Okay. Why do we need them? We need them so we can solve equations, and that's what's coming tomorrow. Okay? That's what's coming tomorrow. Good old algebra. All right, let's talk about the product property. Remember, logarithms are equal to exponents. So when I have the log base b of two things being multiplied together, all right, when I'm multiplying with bases, what do I do with their exponents? I add them. So it's log base b of x plus log base b of y, okay? So if you have a single logarithm and two things being multiplied, you can split it apart, same logarithm, add the two things. So if I had log base 2 of 5x, that's the same thing as log base 2 of 5 plus log base 2 of x. All right, we can separate multiplication with addition. Properties of logarithms, they come from our properties of exponents. Okay, the quotient property, same kind of thing. Okay, if I'm dividing exponential functions, what do I do to their exponents? X to the 5th over x to the 3rd. I subtract them. So if I have log base b of x divided by y, I can split it apart as log base b of x minus log base b of y. Okay. So if we put it just into some non-variable form, log base 3 of x divided by 4, that would give me, bless you, log base 3 of x minus log base 3 of 4. So if we have division within a single logarithm, we can split it apart with subtraction of two logarithms. Okay. And then the last one is the power property. Okay. If I have log base b of some number to a power, we can pull that power out in front as a constant. So n log base b of x. Okay. So let's say I had log base 3 of x squared. That's the same thing as 2 log base 3 of x. All right, we just pull that exponent out in front. Okay. Yep. So one of the things we've got to be able to do is to take them from what we call expanded form into a single logarithm. All right. And that's the way we go most times when we are solving equations. Rarely will you have to spread them apart. There are some times in calculus when we integrate that we do have to spread things back apart. But for right now, we'll just kind of be pushing them together. All right, we want to take all these logarithms, let's make it simple and make it 1. All right, why have 2 when you can just have 1? Okay, so that's what we're looking for, putting it together. So let's look at a couple, then I'm going to let you play with a couple. All right, log base 4 of x plus log base 4 of y only works if the bases match. Okay, so the bases match, it's addition. How could I put it together as 1? X times y. Yep. Okay, not intended to be super difficult. That's what we would do. Okay, we could put them together as multiplication. What about the second one? Log base 3 of 5 minus log base 3 of z. It's subtraction. When I put it together, what would I use? 5 divided by z. Okay, we use division. Okay, so to make it 1, we use division. Now, let's look at C. I've got log base 10 of x minus log base 10 of 5 minus log base 10 of z. All right, what are we doing here with all the minuses? We're dividing, okay? So basically what happens here is we've got this one value that's in my numerator. The other 2 are going to end up in the denominator, 5z. Okay.
Do you know that it's not 5x divided by z?
Because you've got subtraction here to start. So the x has to be divided by the 5. And then if I divide by the z again, it would end up back in the denominator. By fractions. Kelly Beth, if I take x, I'm going to erase this, and I divide it by z, that would be x over 5 times 1 over z. That's why the z goes to the bottom. Fraction rules. Okay. All right, y'all try D and E. And then I really love F. It's a challenge. All right, on D, what are we going to do with that 3 that's right there in the front? It's going to be an exponent on x, okay? That's going to be an x to the 3rd. So this is now log base 2 of x cubed minus log base 2 of y. So now that I just have a single operation, all right, or just addition subtraction, I can put it together, all right? Which operation are we going to use to put it together? Division. X cubed divided by y. Good job. Okay. All right, let's look at this next one. Okay. Got a bunch of coefficients that have got to come up. All right. I'm going to leave that operation as subtraction instead of pulling that b up as a -5. Okay, I'm just going to pull it up as a 5. So I have log base 7 of a squared minus log base 7 of b to the 5th plus log base 7 of 4. Okay, so let's talk about what we need to do. All right, to make it one logarithm, so log base 7, a squared, and then minus a b to the 5th, what are those two things going to do? They're going to divide. So a squared divided by b to the 5th, but plus a 4 would do what? Multiply, so it's going to go on the top. Good. Yeah. Okay, it's going to go on the top. Now, this last one's interesting in my opinion, just because, well, first thing I notice is there's only one logarithm there, okay? But it still wants me to condense it to one logarithmic expression. Well, I can't just make the 2 go away because it's not an equation. I have to find a way to rewrite 2 as a log base 6. Okay, so we've got to think about what number would have to be in there so that when I simplified the logarithm, I would get 2. All right, so here's how we think about it. 6 to the second's what? 36. Okay, I just rewrite 2 as log base 6 of 36. It's still equivalent. Okay, I'm going to keep my plus log base 6 of x. And so now if we want to write it as a single logarithm, log base 6, and what would I do with my values? I multiply. So I'd have 36x. That one's challenging. Okay, we got to think a little bit. Got to rewrite that 2 as a log base 6. Okay, so we have to really be thinking about the numbers involved there. Okay. All right, so when we evaluate those logs. Questions on those first 3 properties? All right, let's look at this question. I like this one too. All right, it says the function f of x is equal to log of 6x. It's a horizontal dilation of the function of g of x. G is just log of x. Show that f can also be written as a vertical translation of g, where f of x is equal to g of x plus k, where k is a constant. Now that's a lot of words, okay? So I'm going to start with f of x, okay? It wants me to eventually write it as this g function plus something. Okay, let's see if we can make that happen. So let's start with f of x. F of x equals log of 6x. All right. If I want to go to something that's been split apart, then I need to split my logarithm apart. All right. If it's 6x inside of there, what would it change to? Log 6 plus log x. Okay. Now, log 6 is a numerical value, okay? It's 10 to some power equals 6. Log x is a variable expression. Well, it happens to equal that g of x that they told me about to start with, okay? So I'm going to replace that log x with g of x. So now I've got log 6 plus g of x. So what's my constant k? K is log 6. All right. If you think about that, that's taking that graph g of x, and I'm adding something to the end. So what's it doing to it? If I take a function and I add something to the end. Okay, what happens if I take x squared plus 4? What am I doing to that quadratic? Yeah, it's a vertical translation. I'm moving it up 4. Well, what I'm doing here is taking log x and moving it up a distance of log 6, right? Log 6 is a number. It's a decimal value, okay? So it is a horizontal, it's a vertical translation, okay? It's a vertical translation. And that's true for every horizontal dilation. If I have a number inside next to x, I can rewrite it as a vertical translation. All right, I can move it up and down. It's just the properties of logarithms, all right, that allows it to do so. The last property that we talk about is change of base. Now, it used to be that change of base was the only way to evaluate logarithms, okay, because back in my day, we didn't have calculators with log buttons, all right? We had to use tables. So we used a lot of change of base, okay? And here's the change of base property. It says if I have some logarithm with a base that I don't know, okay, I can take the log of a base that I do know, and it doesn't matter what that number is, all right, of x, and divide it by log base a of b, okay? So, of the original base. Now, this bottom value is a constant, all right? That's going to be a number, all right? It's a constant in this expression, all right? Because of that, what has happened is that we can take any log function, all right? All log functions, all right? Because that's a constant. It's a number in front of that other logarithm. It is a vertical dilation. Okay, and that's just kind of a cool coincidence that happens because of change of base. I'm going to show you how that works here in just 1 second. Okay. Like I said, we used to have to use that when we didn't have calculators that had a log button on them of any sort, right? And we used tables to evaluate logarithms. We had just tables upon tables upon tables of logarithms in the back of a book, right? That we had to reference and then divide the decimals with a scientific calculator. Right? So if we want to change the base, right? Notice they both have the same base. Whatever was inside the logarithm goes on top. Whatever the original base was goes on the bottom. Base bottom. All right, that's how I always remember that. Okay, so let's take a look at this last, well, close to last one. We got two more after this. So it says, let f of x equal log base 4 of x and g of x equal log base 9. Show that f is a vertical dilation, all right, of g by finding the value of k such that f of x is equal to k times g of x. All right, lots of words. Basically, it wants me to change the base on f. All right, what base does it possibly want me to use? Well, we're going to look at g. What base does g have? It has 9. Okay, so what I want to do is to rewrite log base 4 of x into something with log base 9. Okay, well, to change the base, you got to use two logarithms. So log base 9, log base 9. Right? I want to change it to something with a log base 9. What's going to go in the top logarithm out of the original function? X. And what's going to go in the denominator? 4. Okay? From the original function. Now, let's look at what we've got left. All right? It says it wants me to show that f of x is the same thing as k times g of x. Well, g of x was that log base 9, so my numerator now is g of x. All right? It's log base 9. We just did a substitution there. Okay? It told me that. And I've got my log base 9 of 4. Right? When I divide by something, it's the same as multiplying by 1 over that value.
So is the denominator now our k?
It is now our k. Yep, that's exactly what happened. Our k, we're going to use that whole fraction because it's in the denominator, 1 over log base 9 of 4. All right, we just separated it using algebraic properties. Right. Now, I think the wording on those last two problems is really kind of confusing, okay? So I picked two multiple choice questions that kind of ask the same question, but hopefully a little bit easier to understand as your last two examples, okay? Straight off of AP website, okay? So they would be part of our non-calculator questions, right? So the first one, how does the graph of f of x equal to log base 5 of 3x compare to the graph of g of x equals log base 5 of x, all right? So basically, let's mess with the original, all right? Can I do something with it? So if I have log base 3 of 5x, what could I do to that?
You can split it apart.
I could split it apart. So log base 3 of 5 plus log base 3 of x, all right? So the question's asking me, what am I really doing to this log base 3, all right?
It's log base 5.
Oh, well, dang it, I did it backwards, didn't I? JK. Okay, so f of x, log base 5 of 3x. There we go, let's split it apart. So log base 5 of 3 plus log base 5 of x. So now, what am I doing to that variable function? What kind of translation is it if it's added on at the end? Okay, if it were x squared or, 5 plus x squared, what would that be?
Horizontal.
It'd be horizontal or vertical? Vertical. Anything at the end goes up or down. Anything with x goes left or right inside a parenthesis. So this is going to be a vertical translation, and we're going to take it up. It'd be B. Okay. Let's take a look at the next one. All right. On the next one, how does the graph of g of x equal to the ln of x cubed compare to the graph of f of x equals ln of x? In other words, what are we doing to ln of x? Right? So if I have ln of x cubed, what could I do with that? Pull the 3 out in front. 3 times the ln of x. What kind of transformation is it when I multiply a constant with a function? How does it change it? It's a dilation. Vertical or horizontal? Vertical. It's a vertical dilation. It's horizontal when it's inside next to x. Okay, so if it touches x, it's horizontal. If it doesn't, it's vertical. Okay, that's how I would expect to see those kinds of questions. All right, here's your lesson practice. Yes?
So how do you know there's a dilation or translation?
Translation is addition or subtraction. Dilations are always multiplication of some form. Okay, good question. All right, so here's some practice. You're going to need some practice on looking at what these are asking, okay? Especially the properties parts. Again, pick and choose the ones. Like if you get some things, don't do those. Do the ones you need to work on. So on worksheet A for 210, we're going to do 2, 3, and 6. For worksheet A for 211, we're going to do 2 through 6, and then 12, 14, and 16. And then for 212, we're going to do 3, 4, 6, 8, 9, and 11, 12, and 13. Okay? So that's what I would look at.